multi-decade research on special purpose reactors, and so he's highly qualified. And I'm looking forward to what he's going to talk to us about. And about some of the proposed designs and some of the technology challenges that they face in space reactors and small reactors. And so with that, I'm going to turn it over to Dr. Rao.
Well, I'm getting the projection going as well. I want to start out by thanking you, Marty. And of course, I do not know if two of my co-conspirators in this from there are Katie Lennox and as well as Andrew Zelmer. Katie, if you're there, thanks. You'll see I stole some of your stuff and probably using it here. And
I'm here, DV. That'll be a good thing.
Okay. And if Andy is there, then I'm using none of your ideas, Andy. They don't. They all suck. But other than that, can you guys see the screen?
Yes, we can.
All right. So what I will do here is start off with these images are indicative of two projects that are kind of very closely linked. One of them is called the fission surface power, and the another one is starting up called the nuclear electric propulsion. So this is the cool picture of the fission surface power that I tell you one thing, NASA really does come up with great posters. So this I really love. And in many ways, for those of you, look at what we make as two labs and few labs together going right there. Imagine that we could actually make a difference. With that, what's the context? It so happened, and some things, I guess, come together in many ways, but just yesterday, after 4 years, finally, President Trump signed off on space policy presidential directive. And I feel good that although it's during the end of his term, well, whether he agrees to it or not, it seems like it's the end of his term. But some of the people that drafted this directive, both at DOE and at NASA and others, are continuing into the new administration. And so I hope and I believe that there will be momentum moving this forward. These are the 4 top objectives of the policy directive. One of them is develop capabilities in particular fuel. And I think I'm going to add to that fuel and moderator. And why in a second, why I added that, I think becomes evident in a second. And demonstrate a fission power system on the moon. If Sebastian is on, because he said he might join in, that's something Sebastian is from INL is working on as well. And a third one is technical foundations that will enable nuclear propulsion in space. And the fourth one is advanced radioisotope power systems. Among those, in the lingo that NASA uses, a flight program, in other words, the government has said, this will be a program that is flight qualified. Other things are going to be in the research area, or technology, development area. The only in here, the flight program is the one that is FSP, the fission surface power. And I believe that is the main priority. And I often say that what's your likelihood that you can build a nuclear rocket if you can't build a piddly 10 kilowatt reactor system, right? So I think that is going to be, and in this case, NASA Glenn has a way to pull out pieces together, and they run what is called Compass study. And these are the drawings that they came out of Compass study. Some of that, this main thing here is provided by us, the DOE, and the rest is their vision for how a system could look like. Now, this is what's called a government reference design, but they, as I make it, we go through, industry is the one that's actually going to build this, and their designs, what they propose may look completely different from here. But this is something that's worth having, but these are the kinds of pieces of technology that we're looking at, okay? And the purpose of that is a 1 year, 10 kilowatt on lunar, and the shielding so that people at the, on the surface will not get anything more than 5 rem per year. And so the reason I put that in, I'm sorry, is that's a major part of our, the package. So additional things out there, it's pump loop, coolant, et cetera, they're baselining with Stirling engines. So in view of this, what I wanted to do is spend first few minutes on going through the legacy. Some of you know, the people like me and Marty and others who have actually lived through these cycles have seen some of these data from the past. So, but others that are young and up and coming, you may not have seen some of this. So I kind of want to start with saying the very first reactor to be deployed in space was by US, and that was a SNAP 10A. It's a reactor using let's just say 5 kilograms of 235 enriched uranium in uranium zirconium hydride, and Hastelli was used for all structure elements. Key parts there is that its thermal output is 34 kilowatts, and INL at that time, Oregon West, played a very important role in the testing and all the rest of the things that was done. It was sodium potassium eutectic that circulated through the core, and the outlet temperature of it was 540 degrees Celsius. One of the problems they had was, in spite of thicker
We lost your sound, DB.
Can you guys hear me now?
Yes, we can hear you now.
Okay. Yeah, I got a thing that said you are muted. So for a minute, I got offended even. But no.
No, I'm sorry. That was my fault. I was trying to mute some new people that came in. So I apologize.
So no, that's fine. Hydrogen leakage was an issue there, and it resulted in, within its expected lifetime of 1 year, they were thinking that the hydrogen leakage is going to be about 150 to 200 PCM. If it were to run for because it builds up, if it were to run for a decade, the idea was that it was really going to lose its criticality from that. And then they did have a thruster. It's a cesium ion thruster. When they fired the thruster, the EM interference from the thruster, or we don't know exactly what caused, but it really created havoc, and the whole control system started malfunctioning. And because of that, after 43 days it was shut down, and the whole mission ended up. But the ground unit that they built continued to operate for almost a year after that. A more recent thing from that was Jupiter Icy Moon Orbiter, where we again started looking at a point worth mentioning is that SNAP took nearly 10 years and several full-scale demonstrations, tests to fine-tune, and then finally build the system. And by today's standards, it's several $1 billion. Then in GMO, they went completely away from that, both in SP100 and GMO. They moved into fast reactors because Soviets were able to build many fast reactors, and that too metal-based fast reactors, and deploy them cheap and fast and everything. So kind of went to a fast reactor system in GMO. The trade studies looked at, liquid metal, heat pipe based and gas cooled, and finally down selected to two, the HP and gas cooled, and finally down selected to a direct gas cooled reactor. And they said LM has liquid metal, in this case lithium, has lots of great features, but they were worried that their words were that you can never test the performance of full liquid metal and the gas separator until it goes into space, because the zero gravity of separator is not easy to demonstrate. Anyway, in the end, I actually am wrong in here saying it's a HEU-UN fuel clad, because in the last iteration, they actually, naval reactors made them put UO2 instead of uranium nitride, because they thought there is still some data missing for uranium nitride swelling. So I need to make that correction. But estimated cost was about $2 billion, and plus or minus by today's dollars, and it got canceled because of the sticker shock. And it did want to have two NDUs, nuclear demonstration unit, one for optimizing INC and one for demonstrating as the Admiral test, they'd call it, right? A couple of features that are worth thinking about or noticing here is that if you see the gas-cooled reactor, they were actually using metal for the vessel. The gas was circulating at about 2 megapascal and around 1200 to 1300 K. So they actually have a layer of another countercurrent gas flow to cool the piping and to cool the vessel. That was necessitated by the fact that if they have to do the testing on ground, that is the demonstrate the ground nuclear unit, and going with a full refractory metals like moly and others, you really that presents a big challenge. So they wanted to therefore use steel and do the cooling and rely on that cooling as a way to prevent creep. I thought that's a pretty, we actually built a system trying to see how well it worked. That was part of Shannon Bragg-Sitton's work. I don't know if she's online, but I thought it was a pretty well done set of experiments there. After that, what came out of it was the few of us that are very much emotionally attached to space nuclear and small nuclear plants. We went around asking, if we're going to do nuclear, what are the principles that we have to follow? From that, we came up with what's called a science-based approach. And this is probably one slide. I'll spend some time after this. I'm going to go quicker. Is that the SNAP and others, we started down selecting on the fuels and the programs on what I'm going to call it the past approach, which is each design or some of the testing contributed to confidence, but it really didn't contribute as much. In the end, risk buy down happened between steps 3 and 4 and 4 and 5. That needed full-scale nuclear demonstration. That's very expensive, hence my red. In other words, you have these designs, but you're not confident they're going to work until you went to nuclear demonstration. And most of the people, the funding agencies, get shy once you start talking about hundreds of millions to do nuclear demonstration. An option we turned around on it was the one I have it on the top that says, based on what we know now, let us try to make it so that the need for nuclear demonstration becomes very, very small and it's focused. So these are all the principles you use. You use things that are technologies and cores that is completely, fully ground testable. And you basically do electrical heating and you kind of say, you know what, fuel elements go here. Once I'm done with all the whole plant testing, I'm going to put the fuel and it's going to work. And maybe to gain confidence, you do a separate zero power critical and others, but you don't have to really do full scale testing. For the Admiral test, on the other hand, you may want to do some that says, I am actually going to show the full scale demonstration, but I'm going to only run it for about a week. I'm not going to run it for the whole 1 year because I know I've used materials that where burn-up issues are not very big, et cetera, et cetera. That we thought is one approach to getting there. And we demonstrated that as part of Krusty, many of you know. And in this particular case, I kind of want to do a shout out to, if Steve Herring is on, that he really helped because there are people that came out of woodwork saying, well, you're using this fuel, is that fuel good? Does it need qualification, et cetera, et cetera. But I think many grown-ups have come in and said, no, I think this will work. This is not the best system, by no means. This may not meet many objectives of the future, but it should be able to do the job for this experiment and for showing that things can be done by these methods. So in case of Krusty, what we did was we came up with a very high fidelity design because it's a fast reactor metal. You guys have a lot of data for it. We have a lot of data. And it's as simple to point kinetics as possible. And it's as simple to, fast reactor feedback. And then a lot of effort was spent on 2 and 3, where we actually built, broke, tested all these pieces. And in the 3, we actually built the whole system and used electrical heaters to show what happens. And when it came to 4, then it became down to just getting enough data to confirm that our codes are right and that we predicted well. And the idea there is once we get this physics and others right, you can scale it up, scale it down, do a lot of things, but that benchmark is there. This whole project was done in 3 years. Here is an example. The 128-hour-long test that was done. In here, what was shown, and you've probably seen all these slides at different times, is that we actually took the reactor to temperature, started tripping the Stirlings, and seeing how that causes the power to go down and the temperature fluctuations, everything. In all these were done with no controls at all, meaning it was operating on static control and it self-regulated its power, which assures us because many of the absent doing the whole stability analysis and all the rest of the things, the amount of control theory you have to think about for these systems where you don't have line of sight, you don't even have data access for several minutes, it becomes very it can become very complicated. So this one was to show that you could actually be very simplified controls. This is what was briefed to this test was done by NASA STMD. We started sharing these results. But here is, by the way, before I go to the rest, this is crusty core on the top before test and the crusty core after test. You can see the slight oxidation. The reactor or the core or the test assembly, whatever you want to call it, was run up to 800 plus degrees Celsius. And few times it actually went to 900 degrees Celsius by design. And you can see at the end there was no creep, and it didn't, of course, have too much DPA, but the design always has been after 10 years, the DPA on this is going to be very small. So that's kind of our thinking of this affordable approach. But once crusty was done, we, to be honest, underestimated the amount of resistance from non-proliferation people and the amount of resistance from various different groups. One of the things, today's reality is that the fuel must be HALEU. Yes, there is a little bit silver lining in the language there that says NASA may use HEU if we show that HALEU-based systems are not practical, can't be built, etc. They can ask for exemption, but reality is, if it's not HALEU, it's probably going to be unlikely to be taken up by NASA missions. And another thing that I kind of am not sure it's the right, that HALEU thing is not NASA's decision. That is a political congress, everybody. But one that kind of confuses me a little bit is one fuel for all missions. I think that is a difficult thing to bring along. So for you, I'm showing is that when we talk about various space systems, one way for me to show how difficult a mission is to and this is Dave Poston's slide really, log of the fuel average power density on the X and reactor outlet temperature on the Y. And most of you know, intuitively know that the melting happens on the oxides and others around here somewhere. So what you're talking about is if you're selecting a fuel for something like the crusty mission, which is a very small burn up, very low power density, very low gradients, etc., you need much, it demands much less. On the other hand, if you're going to the NTR, you really have 10,000 watts per cc. And really, the metric I use is that power flow misbalance of about a second is all it takes for the fuel to melt. So designing a system like that is going to be a lot different, a lot more demanding compared to designing a system like the electrical powers, like the 10 kilowatt systems for moon or nuclear electric propulsion. So I think something will happen there, but I'm just saying that we're trying to force fit a lot of these. Probably that's not the best option, and we may revisit and say maybe metal fuels are good, are fine here, but then you need to go to a particle fuel here. What might come out, I don't know. But it could actually, if done right, it could be great that we actually have industry and everybody aligned to make advanced fuels. If it doesn't, then we could kill ourselves by trying to adapt a fuel that's not best fit for missions. Another thing I see is the not invented here, and by that, a lot of times I'm seeing is NASA missions and the various agencies going in and saying, oh, my priority is propulsion with a 1000 ISP because that's what they want for their center or their mission or others. And we, the nuclear engineers, get to play very little on the politics of it. And yet we pay the price because public only has patience for spending, maybe they'll spend several $100 million. If they're not seeing any real hardware, they're going to walk away, right? So we all need to be careful on that. The third one is industry dynamics. Right now, there is a lot of excitement from the industry. Let's get going on the FSP. Let's get an RFP. Let's get this, let's get that. All of that is good. But once you down select, the ones that didn't get are not going to support you. And how is that going to impact? I don't know. And the final one that we have to, and I know I and Katie and others have spoke in the past, is our urge to go back to how we used to do things. That is, we're going to build this plant and we're going to operate it on ground for 1 or 2 years to demonstrate. Those are all great things to do. But recognizing that this first one is a demonstration on moon, maybe we should think about it as saying our demonstration will be just a very short demonstration. And so that I don't have to build a new containment building. I don't have to deal with waste. The reason I showed you that spent core is that right now, what we call the special ops people, they're using that core for doing, how to find nuclear materials, right? Hide and seek stuff. You've got to find a way where you didn't really cause so much damage that you have to get rid of, getting rid of waste becomes a big issue for you. So design those demonstrations in a way so that you get all the data you want, you get the admiral test, you get the regulators as well as the sponsors and the high-end DOE people comfortable that it's not an egg on our face, that it's going to work. But then we have to stop what is that minimum, not what we used to do in the past. With that in the mind, what we've started was, and this is where I did a study, was that looking at what options exist in these about the same mass range for a HEU versus LEU options. These are the 4 things that I looked at. And the conclusions of it is HEU system is the most mature, HEU fast system. And it's not only because of the crusty test, but we know how metals perform. And we've also seen how Soviets have done. So it's high TRL, but it's got political issues with it. On the other hand, the moderator systems are possible, but the peer review team's recommendation is before you exclude and say, I'm going to focus exclusively on LEU, make sure you demonstrate that these moderators can function for 10 years in vacuum, containing hydrogen, and that you can actually predict their performance all through their life. If you don't do that and you go in this direction, you're going to be the same like SNAP, where you try to make a fuel work at high temperatures for which that fuel was not designed to start with. So we got to be careful. And the reason I'm going through that is some of the most important tech math that we are doing is in that general area. So I will not spend much other than this is a nominal or a generic reactor system we used. And those are you that are interested. I know Katie has, as well as others that there have, in particular, all those TRL levels. We spent several days trying to figure out what's the right values that we can stand by, etc. So go talk to her, and I think you'll see our logic on why we assign those. But we've also acknowledged that once you go into moderator, you can do 2 different ways. One is this old Topaz-like. For some of you, at least, I'm sure familiar with this system where the fuel, the red, is in the operating at, whatever temperature you want. There is an insulation, and then the line color is the moderator where hydrogen is. And so hot side hot and cold side cold. And in this particular case, the design is where the moderator is communicating heat to the reflector and stays cool enough. In here, moderator and the fuel are intermixed both thermally and neutronically. In that case, moderators have to take a lot of insult. So we looked at both systems because DOE still believes that some of these are not believes. I mean, DOE's and ours, i.e., when I say DOE, it's labs and DOE. We still believe that this is ITAR information. I'm not going to go into details of the design, other than I'm going to show you a couple of slides to kind of give you what the concept is. So this is one slide that I'm going to say is that here, the one example of it is these are heat pipes, and that's the fuel, and they're in the moderator. You can see the cut. And moderator in this case is a zirconium hydride, 1.65. For those of you that worked in the Topaz program or looked at that, that is the Russian equivalent of that. They actually made that, and we're trying to make that now for demonstrating technology readiness level. And the idea is fissions happen in this fuel, and the neutrons go out, they get reflected back in, they get moderated in the blue, and the moderated neutrons then come back to the core and cause new fissions. So you want to keep that as compact as possible, and you also want to design in. As you can, imagine, therefore, success of this is going to be demonstrated by how well can I keep the fuel, which is at around 800, 900 degrees Celsius, from moderators, which can, take, maybe 500 degrees Celsius in that range. How am I going to separate them? And how well do I know moderator kinetics, the neutronics part of the moderator? So those are the tech mat. And here I'm going to quickly go through, but moderators have been used in the past. You guys have used way before many of you, some of the younger people were born in the aircraft, nuclear aircraft program and others. If you're going higher in temperature, your moderator's choices are going to be either yttrium hydride or cool zirconium hydride. One other one that Brookhaven experimented with is lithium hydride, or recently more calcium hydride. Those are ionic, but then they melt, and you can now use molten or liquid moderator, that's hydride moderator, and use that effectively to rely on its negative feedback. All these moderators have something in common. There is a PCT relationship. At a certain cover pressure, they operate very well at a certain temperature. But if the temperature goes up, then the hydrogen comes out of it and goes into the clad or escapes. So you have to make sure you have enough margin here. One other thing we noticed in our testing is at very low PCT levels, the internal resistance to hydrogen diffusion limits hydrogen release. As a result, they actually remain stable. For example, if I take zirconium hydride and I'm operating around 400, 450 degrees Celsius, cladding and doing the hydrogen barrier is not as important. But if I want to go above this, beyond 500, all of a sudden cladding becomes your own one and only barrier that you can depend on when you're operating for tens of years. So what this brings to you is that you have to think about cladding, this system, which is what I tried to show here, is that the moderator should be thought about as a system. The moderator, the thermal control including the insulation and the cladding that you're using. Another thing about the moderator too, and this happened in the SNAP, is that when you create temperature gradients in the moderator, the hydrogen actually migrates from, in this particular case, higher temperature to the lower temperature. So these are concentrations and those are temperatures. Red there means hot, that's cold. Blue here means less concentration versus high concentration. So for a system that is designed with 1.6 as the uniform, because of this temperature change, you could actually see somewhere around 1.66 here and 1.58 there. And for zirconium, it's not a big deal, but for yttrium, because yttrium also eats neutrons, this type of distribution can actually eat into your reactivity worth quite a bit. Think of where yttrium is in the middle at low hydrogen density. It's going to eat all thermal neutrons, but it's not going to slow down as much. So these are kinds of things that we got to think through. I joke often saying we have a way of, my joke is I hold material scientists in contempt, because the moment we get into a nuclear project, it gets taken over by the material science people, and we don't get the headroom that's needed to actually make measurements that are needed for neutronics so that you can smartly design the system. Instead, we get forced into saying, oh, that's just an issue that you just have to look at, and you can actually put sensors so that if the power is oscillating, then you control it. So this is, by the way, for those that are nuclear data people, the hydrogen actually exists in a Maxwellian distribution. These are what are called S alpha beta cross sections. And this is the first time that S alpha cross sections are being derived now. They were there for zirconium hydride. Now we are doing that for yttrium hydride. And in doing so, we are using density functional theory to come up with it. We haven't really verified them yet experimentally. And the one final point I'll make on the moderators, why I keep harping on, is in Topaz, the moderator, the way it was designed, is that feedback of the moderator is positive. You guys look at it, that's dollars. So in Topaz, if you start the control system, the drums, right? You start going up in temperature, and guess what? The zirconium hydride starts getting hot, and all of a sudden you're going positive. Now you need to have a control to rotate the drums back to actually beyond where you started, so that you're now quenched that, and so that now you maintain a equal, neutral reactivity. It's not a difficult thing. You can put a sensor, and they had that in SNAP as well. You could put a sensor for temperature and say, if it's getting too hot, rotate the drum this way. If you're getting too cold, rotate the drum that way. It's an easy enough, but you don't know the stability where you will be all the time. Another issue that we found in SNAP is that initial instabilities that you get here, even after you overcome, due to hydrogen redistribution in case of SNAP, what you see is that temperature goes up, hydrogen starts coming out, and now you have to adjust the drum again, go back up again. But with time, as they reach a steady state, the duration or the time gap over which you need to get these adjustments becomes less frequent, but you still have to worry about those dynamics. If you don't design it right, you can actually go into power oscillations. This is my thing. If any of the developers of Moose tools are there, we've used both Moose tools as well as Abacus and others to show this. For the design that I showed you, there is quite a bit instabilities initially. Once you reach steady state and you operate at the steady state, even if you trip the Stirlings or power conversion and all the rest of it, it rides through without needing any additional control. But you've got to be really careful that you designed it and that you're really able to assure stability of the reactor. Because if something went wrong there, you don't have time, you're not there. So it's got to be automated. And I don't like automation unless I know that the reactor is absolutely stable. Towards that end, we're starting to do some tech mat. And by the way, I should be done in the next 10 minutes, and then I'll open it up for questions. Here, what we're doing, actually, this is pretty interesting stuff, is that these are yttrium hydride discs, and that's moly, the outside. We stacked the yttrium hydride discs in moly, and we sealed it all together. Moly is a pretty good keeper of hydrogen. And now we heated it. This is where we put the heaters on the top, on the bottom, and heat the hell out of it. And similarly, we are making these for the zirconium. That is zirconium, and that is zirconium 1.6. You see there is a little, if Steve is on, that is Herring. I was telling you when we met or on phone that we are making this, Steve. We still have some imperfections because I think we hydrated them too fast. The newer one came out better, but we're trying to do that. But most importantly for the nuclear engineers here, we're trying to put these assemblies together with existing nuclear materials on our criticality machine to kind of see how does temperature-driven reactivity oscillations occur in here. So to that end, we actually have an experiment sponsored by the NE, and in this case, I thank Jess Zine, is that we are actually going to be building we built already. It's due to COVID, we're running late on that. But these plates are what those different colors are. Along with that, we put few moderators and few fuel samples. We're going to first test run and show how good it is before we want to do a real benchmark level experiments on it. I feel without getting data like that, designing a control system is going to be asking for trouble. So on the instrumentation and control, we're doing the same thing. Once we get data from there, and this is actually being led by Andy Zolmer, one of the things we're trying to understand here is if there are any of you that they're from SP100 days, the multiplexes and just the instrumentation cables used to weigh quite a bit. I actually carried one of the multiplexes with instrument cable, and well, I'm not a very weightlifting kind of guy. It's a pretty heavy thing. Instrumentation cables for the SP100 combined weighed about 150 kilograms. And I think Andy said if you want to go with tested cables, they're going to be about 2 to 3 pounds per foot. So we have to figure out a way to come up with cables that are going to be lighter and can still withstand not only neutron radiation, but plasma and charged particles and those kinds of things. That's another area we believe there is a disagreement here. Some think industry has all the solutions for it, and Andy, we keep arguing that that's not true. So that's one area where if we get money into TechMat, I see that you guys some of you guys sitting around there at INL will be playing a pretty important role. Traditionally, Oak Ridge try to do that, but I don't think they have all the capabilities these days. So if we get the money, that is something that I have to work with to figure out how best to get this work done. But one of the other things we may have to do is, do we need to get some of these materials irradiated in either one of the reactors? In this case, I just funnily had one of the people I work with got his degree from Ohio State University. So if you noticed, I put D, Ohio State University, because they're very proud of that D part. Once we get those tech demo done and provide that with the industry, this is my last slide on the FSP, or actually most of them, is that's what you're looking at. They actually are able to go in and predict the lighting and others, where a potential location where they may demonstrate this, sun on you really can't get much solar, and trying to locate this. Imagine us there putting our technology there, I guess, is how I'm choosing to end on that. And another aspect is that along with that, coming a new mission that NASA is thinking about, it's called NEP, Nuclear Electric Propulsion, where the idea is you generate about 2 megawatts of electricity that can be used by propulsion systems to move us from Earth to Mars. That's another program that's getting started. I think they are trying to explore, you probably know already, there is an NTP program. This one is an alternative to the NTP, trying to see, can they do NTP? If not, what's their risk management approach? Those are all my backup slides. With that, maybe I'll end on this one here. I'd like to say my prepared presentation is done, and I'd like to engage in questions if you have any.
Any questions for DV?
There are a couple on the chat. Or one question and a comment so far. DV, can you see how to get to those with the little?
Yeah. I am on the chat. It's loading. Why not plutonium, Dan Thomas? Why not? Even with HEU guy, we are having so much trouble with the interveners. So there's nothing other than that. We really love plutonium type. It's from the question, I'm assuming that you haven't dealt with the intravenous groups yet. So nuclear engineering is too much controlled by what we can't do, not by what we can do. What's the best solution? Having said that, there is another aspect to it, is I am not a very big fan of having plutonium in space systems, because as you start going up very high temperatures, I don't know if you know, but plutonium has pretty bad thermal conductivity in many ways. And once you put that in uranium or others, you really start tanking in your thermal properties. So I personally haven't looked into all of that. The main reason why we don't do it is because we don't want the people coming out of woodworks protesting that. Fuel type has been a discussion ANS, as they have been working on a position statement. So that John Best, thanks, by the way. I heard you were actually involved in that. I know you guys have tried, and all reasonable people have tried. I think I summarize the IANS thing is to say, when reasonable or when practical, use HALU. When necessary, use HEU. I think now the burden of proof for when necessary is you have to go back to the White House and Congress and show them why it is necessary, not because you know, a reasonable guy like Matty or any of them says it's a good thing to do. So I really think 233 and others make a really compelling cases, but I just don't know. As of right now, my thing is to show through testing whether moderator systems are possible, as in really possible. Can I run them for 10 years? Nobody has done that. And we're trying to design a mission around it. That really worries me, right? It should worry everybody. And once that is done, trying to see if I can deal with HALU. If not, I think we will revisit some of these. Will NASA revisit? Okay, so I'm not an expert at all in ion propulsion. I do know they're looking at various ion propulsion systems. You may want to actually, if you have interest in that, send me an email when they have what is called TIM, Technology Interchange Meeting. They give us so many slots from the labs. I will, and if this is an interest of yours, I will try to get you on that TIM. That's all I can tell you. I am not an expert. In fact, I'm starting to realize I'm not an expert in anything. But so that's another one. I'd be glad to put you in touch. Another person to talk about that is also Doug Burns. He is involved a little bit on this project as well. So what's the feasibility of into the celestial direct? I don't even know what. So thanks. That's a great question. So they asked the industry and they asked the labs, would that eliminate load? Because, so let me say the question. The question is, when you land on moon, do you need a radiator? Can't you just use, pump the liquid down into the moon subsurface and cool it, right? That way, maybe you minimize the amount of weight you carry. So let me, if you guys can still see my slideshow here, one of the things we have to show is that heat coming from here will not have any impact whatsoever on the surface of moon. So we not only can't use it, we have to make sure it doesn't impact. That's our design. That's part of the space policy that all the governments across the world have signed, that when they land on moon, you don't own moon. No, you're not given rights to moon surface. Neither will you be able to, should you be thinking of disturbing anything until they change that. Now, ISRU, where you're actually digging water from there and making hydrogen, etc., will obviously impact that, right? So at least for the demonstration mission, they do not want to do that. They also do not want to use materials that are there as shield. They want to carry shield with the mission. I hope those are the only 4 questions I've seen.
Okay, come on. Any other questions for DV? Well, if not, our time is up, and I'd like to thank Dr. Rao for his presentation. I thought it was very interesting. It's great to see what's going on in the world of space nuclear from 10, 15 years ago when I was actually doing something in that area and dabbling. I appreciate your time and presentation. We have recorded this session, and so if you want to go back and look at that or you share it with others, we'll make sure we get the URL for that recording out to our membership. And with that, I'll wish you all a good day and happy holidays. And thank you for everyone for being here and being part of this. And
Thank you.
we'll go from there. Thank you so much. Bye.